This is AP Calculus, Unit 1, Lesson 7. We are in Standard D because, I just clicked on the wrong button. Go away. We are almost done with Unit 1. We have 3 more lessons today, and then today's Tuesday, so Wednesday, Thursday, and then Friday we're going to start doing some harder problems, some like AP problems. All right, so we're still on Standard D, instantaneous rates of change. We're starting to talk about the real calculus ideas now, finally. So yesterday we talked about average rates of change. Graphically, what do I have to do to find the average rate of change? Shout it out.
Draw a line between A and B.
Yep, draw a line between A and B. I need to make sure that I color code the heck out of this thing. So I'm going to make black my default color. If I draw a line between A and B, or f of A, comma, f of A, and B, comma, f of B, these 2 points, that should be the average rate. And I'm really wanting them to be better. That looks better. So this represents the average rate. The slope of that line is the rate. And assuming that the average rate holds for the entire function, that's perfect. So that we already know. I want to go by another name, though. This is also called a secant line. You'll know a secant line when you see it because it intersects the function more than once. That's the definition of a secant line. You can see that it intersects down here at A, up here at B. And I want to teach us the other type of line. Do we know what other types of lines we have from geometry? Secant versus tangent. So let's find a random point. Oh, look, I have C1 and C2 labeled for us. I'm switching to red now. Red is for tangent lines. So if I come up above C1, I'll make a point here. I need to find a line tangent to this point. And this is a weird idea. Usually you need 2 points to make a line, but now in calculus you need 1 point to make a line, and it's the tangent line. And how do you find the slope of that tangent line? We'll talk about that in a sec, but do your best to estimate what would a tangent line at this point look like. And it will hopefully only intersect that function once. And I will do my best interpretation of a tangent line, which looks, okay, I'm going to get the slope right, and then I'm going to move the line. I think the slope looks roughly like that, and it goes through that point. And I can make this slightly longer, like that.
Couldn't it just be like a vertical line that's on the y-axis?
A vertical line.
Just a vertical line,
like this?
X equals 2.
Okay, yes, you would be correct in saying that that is a tangent, but okay, so actually you wouldn't be correct in saying that's tangent, because tangent has to be at a 90-degree angle too. That's part of the definition of a tangent line. Like when we were in geometry and I drew a circle, well, I guess I could have used technology, but this isn't a tangent line to the circle. This is a tangent line to the circle because if I drew a radius, that radius would intersect that tangent line at a 90-degree angle. So one of the definitions is it has to be at a 90-degree angle from the radius of a circle. So it should look like it is kind of parallel to this point. It should be going along the same slope. Yeah, but good clarifying question. So it doesn't have to have roughly the same point. And then do your best also to make a tangent line at C2. Just get some practice drawing these, because I think, let me just double check. Yeah, you have to draw quite a few of these tangent lines in the homework. All right, so I'm going to do my best attempt. Hey, not too shabby. I've definitely done worse ones. So those are tangent lines. So if a secant line represents the average rate of change, what does the tangent line represent then?
Rate of change that one is.
Yeah, and you're using that key word from our title, right? The instantaneous rate of change. And yeah, and that's exactly what I want to label this one too. So this is the instantaneous rate of change. Instantaneous rate of change. And I guess I should have moved that word up, but rate of change. And again, just remember that secant is the average rate. And that's at one moment, as if instead of having my moment defined between 0 and 5 seconds, my moment is I can't pronounce this word correct, infinitesimally small. It's between 0 and 0.0000001 seconds. It's a very small amount, smaller than I can even comprehend. So this moment of the function, we can actually represent the slope with some notation. But before I do that, I remember that we need to review from yesterday. What is the slope of this secant line? What was the formula? If I have b's, f of b, stuff like that, that secant line slope was?
F of B. Yeah, B minus A. Over B minus A.
B minus a. Perfect. That was the slope of the secant line, so I can make a note here. That was the slope. So the slope of our tangent line, I'm going to do it over here on our second line, is going to be f prime of C2. It's C sub 2, I guess, if I'm pronouncing that right. And that's how I read this, f prime of C sub 2, or C2 if you're being lazy. So I guess I can do that in green. It's the prime. F prime. That's how I read that little symbol there. All right, so, and that is how fast I'm going at that certain moment. What is a key thing to remember here? So let's do a little start here. So if I am looking at, I'm going to do a bunch of synonyms here, so get ready. Instantaneous rate. Is synonymous with, so is equivalent to, I'm just using an equal sign here. I'm combining English and math, oh gosh. Is equal to the derivative. It's supposed to be an I. Derivative, which is also the tangent line. Which is also equal to just f prime. All of these things are the same in different forms. So instantaneous rate is the label that we give it. The derivative is the symbolic way of, like, what are we doing? I guess it's still, I guess this isn't really symbolic. This is the symbolic version, f prime, but this is how to get, I guess. And then the tangent line is the graphical representation. All of these things, taking the derivative, finding this tangent line, that's what we're doing. All right, so let's talk about what it means to take the derivative, specifically where you can't take it. So that's a better way of defining it. So this section is called differentiability. That's a mouthful. Differentiability. All right, so where does the derivative, where does f prime, where is that instantaneous rate or that tangent line, where does it not exist? And the fastest way of saying that is f prime. Where does f prime not exist? D and E. F prime does not exist at the following four things. Number one, endpoints. And I do want to think about this kind of logically too. So if I have a function, you don't need to write what I'm about to do here. I'll do it in green to let you know. This is just to picture it in your minds. If I have a function that has an endpoint, we don't know what the derivative is, because what if the slope all of a sudden changes? Or what if it just, there's no side that exists over here? We don't know what's going on. We have to know what's happening on both sides of the point to know what the slope is of that point. All right, so endpoints does not work. 2, sharp corners. The logic behind sharp corners, I'll do this in green also. If I have an absolute value graph, we've seen these V-graphs before, and I'm looking at this point right here, that's a sharp corner. The slope looks like it's 2, slope is 2, slope is 2, slope is 2, and then all of a sudden it magically changes and the slope is -2, -2, -2. And if you have a magic change without a gradual change of slope, that's a sharp corner. That doesn't work. You need in calculus to have a constantly smooth, curvy function in order to take the derivative at each point. If the slope on the left does not match the slope on the right, you have a sharp corner. You can't have the derivative. 3, discontinuities. Discontinuities. And this is a review of lesson 1-4, continuity at a point. Do we remember what the 4 discontinuities are? We'll list them here in the notes again. List of 4. Shout them out if you remember any of them.
Hole.
Yep, that's one of them. Holes. Breaks.
Asymptotes.
Careful, it's
Vertical asymptotes.
only vertical. Yeah, not the horizontal. VAs. And what's the 4th one? Gaps, yep. If you have any of those discontinuities, then it's not, you can't take the derivative, which is kind of a cool idea, right? In order to be differentiable, in order to take the derivative, you have to be continuous. That is, you can't have any discontinuities. So if you have any discontinuities, it immediately means you can't take the derivative. That seems like a simple idea now, but once we get into calculus, it becomes a much more powerful idea later. It's like, oh, well, stop right there. We're done. You can't even take the derivative. And finally, 4, vertical tangents. And this makes logical sense too. So if I have a graph, again, I'm going to do this in green, that looks like this. If I'm looking at this point right here, the tangent line will look like that. I mean, you can represent that with a function like x equals 1 or something. But the problem with this is we can't find the slope. The slope of that line is infinity, yeah, or undefined. That's the reason we can't do vertical tangents. Whenever we have infinity, as Ben said, we usually in calculus just say it does not exist. So those are the 4 things. Memorize them. You should have already have these 4 memorized. It's a good review, but these also need to be memorized.
You know what I just realized?
Yes.
So in Inkscape, when you're drawing with the path tool, which I use a ton, it's actually entirely based on tangents. It's how you make the curves.
How so?
Let me show you.
All right. You want to use the Mimeo? That way we can record it also. Oh, no, you want to show it on your laptop? All right.
Well,
Ben was just showing us how in Inkscape, if you drag around the, I don't even know what these are called, but the modifiers for the curve in Inkscape, the handles, you can actually affect how the derivative is acting at each of those points, how the slope changes for each of those points. Yeah, that is exactly what's happening in our lesson. All right, so after we talk about where it does not exist, then we have nothing else to do. That's it. So go ahead and write your summaries.